begin the day by correcting my yesterday's mistake, which is actually with this slide. When I showed this, the left-hand side was the for flight one for two different earthquakes, so a weak earthquake and a strong earthquake, but both are for kinematic load only. Whereas on the right-hand side, it is the kinematic plus inertia. I may have said it the other way. I may have said these are for bigger earthquakes. Uh, so I thought I should correct that. We also saw all these equations yesterday and how poorly the existing methods in literature perform when it comes to kinematic uh, bending moments, estimate of peak kinematic bending moments. And I briefly mentioned that uh, although we made these calculations using the author's equations, we were using the as we are supposed to, and as you would in yeah, if you're a consulting company, taking uh, the shear modulus of the soil at small strength, because that's all you will know, because you don't know what happens to the stiffness of the soil under a particular earthquake. However, a couple of authors came back to us and said, ah, maybe our equations will work better if you guys actually did this uh, correction for shear modulus. So we had a go, and I'd like to share that with you unofficially because the paper is under review. You submitted it to the geotechnique and it's been reviewed. So in theory, I should not be showing any of this, and I certainly can't give you copies of it. But I can certainly share amongst friends, as it were. So what we did was it's exactly the same stuff as I was talking about, except ah, these are the few things I wanted to share. So it is possible for us, uh, if you remember from yesterday, we are measuring quite a lot of. So if I have like a in our container, we have the large dense sand. We've got lots of accelerometers where we are measuring the accelerations uh, during shaping. So if I know the accelerations at these locations, that with as a function of time, I can work out the shear stress as a function of time. Because I know the mass of each layer and I can work out how differentially it's moving. So I can work out the shear stress. But because I am measuring acceleration, I can double integrate that to get my displacement. It's basically double integral of that with some careful application of the boundary conditions. You should be able to get displacements. If I know all the displacements, then the strain gamma is basically value by 1 plus b equal to x, I believe. Okay, so we should be able to work out the strain as well. So I'll get the strain history. If I know the stress and strain, then I can plot my loops for tau and gamma. If I know the loop, I can then work out the slope of this, and that gives me my G is tau over gamma. And we can do this for every cycle of the earthquake. So once I know the G, I can plot this. So I can say what is the strain and what is the shear modulus as normalized to the initial modulus. And clearly people know that this kind of degradation curves happen. This is, we are not the first ones, everybody in the world knows these are the shapes of the curves you get. So we can plot our points from the experiment onto these for different depths. So here is one for a depth of 6.9 meters, and you can see our strains are between maybe 2.2 to 0.3 percent, and you can see how much degradation we got. And you can compare with methods existing in the literature, very well known ones like Uchtik and Dopri or Darendelli curves. And what we discovered was we're closer to the Darendelli curves, which are more for clay, normally consolidated clay. So now we are in a position to actually apply the corrections the authors were, of the other methods were asking us, because we now know how our stiffness is degrading with the earthquake cycles. So that's for 6.9 meters. We did the same for 8.7 meters, and they're all coming pretty close to the Darnley curves. At very large depths, it seems like about 10 meters, we are somewhat deviating, especially at small strain, from the Darnley curves. But that's to be expected because the Darnley curves are all derived based on triaxial pairs, and we are doing this from using centrifuge. Okay, having done all that, this is the ultimate figure I wanted to show, which is we're still nowhere close. Some after we allow for this correction due to nonlinearity in soil, a few of them come close. So the dark dots are the centrifuge results. In the plot I've shown you earlier, they were very far apart, whereas now, after correcting, there are a few which go completely crazy. For example, if I pick up this Nicolau, Gadgeters and other people, 1995, which is their modified version, that has put these up here. It made it really, really bad. Whereas the other ones seem to come a bit closer. Now this box is basically an expanded version of this. So you can see still, if that is the centrifuge data point, still we got big variation in that. But the one which is coming closest is a co-author on our paper. I may as well declare interest at this point. So our co-author of this paper insisted that we include this so that he can claim of all the bad methods, his was the best. Fair enough. I have no dog in this race, as they say in English. We have the data. Now, if there are people out there who want to propose equations, we can compare for all different cases, smaller flakes, larger flakes. And if they come close, good. If they don't come close, we'll say you haven't come close. So, for the first time in last 15, 20 years, where people have been working on trying to estimate the kinematic bending movements, we are in a position to compare whatever methods people have proposed to some reliable data set and say you guys are close, you're not so close. And that's the main point I want to make. So two things come from this work. One is how do you use the methods in literature? So the methods available in literature should not be used blindly with small strain shear models. You must correct it for soil nonlinearity. And you can do that quite easily because you will always have some design earthquake in mind, and you would expect maybe 0.3G, 0.4G, whatever it is. You know the peak ground acceleration that you're designing for, and you use that to find out the equivalent shear strain and correct the small strain shear modulus for that. So if you're doing finite element analysis, in theory, all this should happen within itself. Because in a FE, if you use the right constitutive model, it should be able to degrade your stiffness modulus proportional to the strain. Not all uh, programs or platforms are having the best constitutive models. There are much better ones than the ones that have been programmed in for you. So I thought I'll start the day by making this one extra point, which I didn't quite make yesterday. And also I was in a bit of rush, so I made a mistake in one of the slides, so I thought I'd correct myself. Okay. Are the points clear this morning? So the important thing, take home message is take soil nonlinearity seriously. And even if you're using methods in literature, they seem to do a bit better if you allow for soil nonlinearity. Good. Now I got that off my chest. Go ahead. Just that. Today, I'm going to focus on, for this lecture and the one later on in the afternoon, on piles which are subjected to instability by virtue of their axial loads. We're not going to worry so much about the lateral loads for today. We'll do that tomorrow. Okay. Now, let me start by saying, why is this important? Now, as I said yesterday itself, you don't make piles for fun. The piles are there to carry structural loads from the superstructure into the ground, into competing ground. So they are quite heavily, or you should expect them to be quite heavily loaded in the vertical direction. Now, earthquakes is an unusual loading that comes laterally on occasion, but their daily job is to carry the load from the superstructure to the ground. So you'd expect them to carry big vertical loads. What we want to focus on is unusual situations the pile can get into because of the loss of stiffness in soil. So let's start by drawing. I got it. Let's worry simply about a single pile. And typically, you'll probably have your pile cap buried up there. I'll call this soft soil for now and stick. That's the most common configuration. Now, first thing is, say we call this pile, the diameter of the pile. How deep do you think you can drive the pile here into the computed medium? You have to go through the soft soil. There's no option. Obviously, you will because you are carrying straight. So the V is big. Yeah, vertical load. Firstly, how much vertical load per pile do you think you normally would have? Any idea? 500 kilograms, 1 ton, more, less. I'm going to tell you, let's imagine this pile to be about half a meter. So it's not quite large pile, but let's have that in our mind. 500 kilonewtons to 1000 kilonewtons on a single pile. So this is where the senior academics will have an advantage, I'm sure, because they would have seen a few numbers. 500. Let me write this down. Is that what you're saying? How much are these numbers out by? Factor of 2, 3, 10. You're saying that each pile you're going to apply, come back to the old English units, right? If I divide that by 10, I'll get tons. So 50 tons to 100 tons on a single pile. On a half a meter diameter pile, that's a lot. So maybe of the order of 100. That's more realistic, especially if the pile is of sufficient length. Is that okay, madam? Yeah, that's about the numbers we would, maybe 20 kilonewtons if you push it, but sorry, 200 kilonewtons if you push it, but not much more. So part of the engineering is to try and have an idea of the numbers. They're not just numbers, This is engineering. We're not physicists. So when we say a half a meter diameter pile, then you should have a rough idea what's the compressive strength of concrete or yield stress of steel if it's a tubular pile, and what can I reasonably apply just from a concrete point of view, let alone the soil and the load carrying. So don't just make up numbers. Now, let's imagine that this length is of the order of 10 meters. It could be 10, 15, 20 meters. That kind of length is quite normal. Now, if that's the length of the pile, how deep do you think I can push this into a completed medium? If it is rock, then I'll rock socket it. That's a separate case. We'll talk about that a little bit later. But if I start with, say, let me say, 10 cent. Yeah. In terms of diameters of the pile, how deep can I push it? Hmm?
1 to 2 types.
1 to 2 diameters. Yeah, be brave. You have a gun, right? 1 to 2 diameters is probably too small. This is in order, if I expect any horizontal loading on this at all, people worry about length of fixity into the pile. In other words, like what we were saying yesterday, below the length of fixity, even if I push this to the center of the earth, the pile has no effect. So you only want to go up to the length of the fixity. There's a guy called Andrew Bond who did some work on this, and he recommends between 5 to 7 diameters. So that's what I want to do. It's a bit small. Okay, this should be of the order of, let's say, 5 diameters. If you ever been to a site where where they're driving the piles, which I suggest you do, normally they say the pile has reached its refusal depth. That is, you bang on the top of it, you will be yielding the head of the pile, but it won't go any deeper than the reached refusal depth. Usually that governs how deep you can go. But if the soil is a bit iffy, you can reach 5 diameters reasonably easily. Rock, of course, you cannot do any of this. If this is the bedrock, you basically bore a hole and you rock socket the pipe. So now we are getting somewhere with this. We know the bit of the pipe which is in soft soil, and we know some idea of how deep this can be. So it can't be anything like that. I'm going to call this that 5. So that's about 5 diameters to make the picture look like. Okay. Now, given this is how we will end up, if it's just a single file, simple case, this is how it's going to look like. A few questions arise. Firstly, what happens if this soil is really soft? Say, like the Tejash's work I was showing you yesterday, we got clay, which is of about 5 or 10 kPa undrained shear strength. So Cu of 5 to 10 kPa. Now again, numbers matter here because I'd always use the example of toothpaste. Now, what would be the undrained shear strength of toothpaste? You think? That's a good thing. Every day we use it, so we know you can squeeze it, it'll come out. But yet on the brush, it won't flow. So it has clearly got some strength, right? So the toothpaste would have about 1 or 2 kg. So we are talking about stuff which is about 5 times or 2.5 times stronger than toothpaste. Clearly quite weak. Yeah. Now, if I have 10 meters of length of the pile, and let's say it's a single pile just with a pile cap on the top, and I'm pushing it in, do you expect much support from this soil in holding the pile? Okay, let's go completely. Let's make it 0. Suppose this is not there. This is just thin air. If you're a structural engineer, would you make a column which is 10 meters high, 3 floors high, unsupported, half a meter diameter column? You won't, right? What would you worry about? Buckling, right? Maybe there's it's not it's an instability issue. So normally with piles, you do not worry about this because you've got soil, and the soil can hold things together. There are a few things I need to tell you about buckling, which I'll come to later on. But normally, in routine design of piles, nobody thinks of them as columns because we are all aware we're driving into the soil and the soil will support. But people started worrying about buckling of piles, particularly offshore, because the clays can be quite soft, like 5 or 10 kPa. Okay? And there's a bunch of work which has been done by Meyerhoff, Walsenker, mostly Canadians who are worried about this buckling. And there's some nice papers out there. You can look them up. But nobody in the right mind were looking at buckling of piles in sand. If this is instead of being soft clay, this is sand, even loose sand, people said, fine. We've got sand. Sand is typically 2 orders of magnitude stiffer than clay. Will be fine. And quite right too. So if you want to do any experiment or calculation, you'll find buckling is not an issue, except when we get into liquefaction. Now this is a bit tricky. Why? Because when we start our earthquake, this is still sand. But the pore pressures increase and our stiffness is degrading as you progress through the earthquake. So you got a situation where you start solid, you turn into something like a semi-liquid, and then if you leave it long enough, it'll again become solid. So before the earthquake, few minutes after the earthquake, you have no problem. However, what matters is the stuff in between, and that's what we'll be looking at. So we want to look at the instability of these files under this very short time frame from the life of structure point of view, but it's quite important from an earthquake perspective. And if I put this in display. Now, as we've been doing in all the other days, let's look at what happened in the past. That's always a good indicator. No. It's okay. This is what it comes up. I'll just use mine. Okay, good. Fine. Ah, that's what. Yeah, perfect. Thank you. Ah, this one has a switch. I didn't realize. Now, there are many. This is a famous case of shower bridge that happened during Niigata earthquake. Now, there are very many nice pictures about this, and I'll tell you a funny story about what happened when we tried to analyze this as well. Uh, this bridge was brand new when the this earthquake happened. They just about opened it, and the earthquake happened. It all collapsed. Now, when they, uh, as I said, one of the things the Japanese are pretty good at is going and doing the post investigation uh, after the earthquake. They pulled some of these tubular files and observed where they deformed. So they were getting this kind of files, and they identified which of these files actually got that shape along the all the spans that have collapsed. And this all was done by a man called Hamada, and he was very respectable big professor. And more recently, these people have written another paper. I'll come to that. This Takata and all reported this. When we looked at this bridge failure, we thought this could be a very nice case to look whether this pile buckling is a real thing or not. Now, I'll come back to this bridge because it is very unusual and rather foolish design, if you ask me, for the piers. What they have done is, if I look at the cross section of it, so that's the pier. You have the pier base, and pier bases are all supported on a single pipe. So as I go along, single row of pipes. So that's the 3D version of it. You've got piles, but they're all along the same center line. So when it comes to this rotating, or falling, you've got only one pile effectively. Normal bridge design, you'd expect modern bridge designs will have deck, sorry, the bridge, the pile cap, and two or three piles, at least two. This way, you will have more rotational stiffness. Just because the decks are trying to go backward and forward, it's never a good idea to have one row of piles. But this is 1964 design, so we'll cut them some slack. So this bridge is particularly vulnerable for this type of buckling failure because you got this vertical load, you got the horizontal load, you got the moment, and you got liquefiable soil. So it's the worst of all worlds. No wonder it failed. But it's not just this one. There are other piled buildings that also fail. But let's just keep a focus on um, piles going through liquefiable soil. Kobe earthquake incident also showed many buildings failed because of which were supported on piles. Now, there's no argument that buildings have failed which were supported on pile foundations. The argument is what is the failure mechanism, and that's where we will go next. But it's not just the Japanese. At Kandla Port, I think I've shown you this earlier, also were supported on pile foundations. This is the Harbour Masters Tower. So, and the whole tower rotated by about 10 or 11 degrees. And if I show you the corner of that, they expose the pile, and you can see the pile has actually punched in. This is also indicative of that we are in. There's a lot of rubbish already dumped into a newly dug hole. Newspapers, plastic papers, and all that. But ignoring all that, it certainly was a problem. But these piles actually, the uh, soil conditions in Kandla Port are such that you got soft marine clay on the top, and there's no bedrock. The clay gets stiffer and stiffer as you go deeper and deeper, but you'll never reach the bedrock. Bedrock is some 150 meters below. No pile can go that long. Incidentally, the rest of the piles of this were designed by my former supervisor, P.S. Chandrasekhar. So he was quite anxious that the berths and the wharf structures performed well, which they did, because those were steel jacketed piles. But this building obviously just is on onshore and is on concrete piles, which didn't do so good. There are other cases. For example, this is a famous case of what's it? They have a name for this building. It escapes me now. It's a big building. It's housed quite a lot of important offices, and as you can see, when they dug out the piles, they saw where they failed. So one failure was there. You can see there, and also when they extracted this one, was forming there. So this is reclaimed film going through sand into sandy silt. Now, if you imagine for a second that we're all structural engineers and we are going to remove this and have that only, then we can solve this in no time at all. Because all you need is Euler's buckling equation and say, right, my unsupported length is maybe 10 meters. Let's work with 10 for now. And that will give me L. And beta will tell you what is the fixity condition. And in our undergraduate classes, we all learned Euler's critical load equation is pi squared EI over beta L square. Now, the value of beta is something that's important. Uh, um, First important thing. The other important thing is L. Now, do I take L to be this length? If you imagine the hinge to form there, or maybe a little bit deeper. That's a decision you need to make. Okay? But it will be some function L or L plus maybe 2D or 2 diameters or something like that. Because it's a buckling calculation, you always tend to be quite conservative. Any half decent structural engineer will tell you don't go anywhere near buckling load. Okay, because there are so many uncertainties, it's an instability. You never want to come close to buckling load. Now, how do we determine this beta? The beta is comes from the uh, way in which the piles can buckle. For example, here, I have that, but typically you'll apply a factor of 4 or 5 uh, on Euler's critical load. So your applied load must be at least a factor of 5 away from the buckling load for the column, approximately. Now, EI is the flexural rigidity of the pile. We're quite comfortable with that. And LE, as I said, is the unsupported length. Now, that could be just this bit or a little bit more. Now, the other point is the beta and how we determine that based on the end support conditions. If I have simple cantilever like this, which is what I'm imagining, then the mode shape in which the thing can buckle is something we teach our undergraduates. I'm sure you learned this too, where you simply complete the mode shape, right? So if I reflect it, I got that to be half a wavelength, isn't it? So if it's half a wavelength, then beta will become 2. So if I go back, if I make beta 2 in here, my Euler's critical load will come down by a factor of 4. So this is getting a bit dicey. So we want a factor of 4 on that, and our critical load is already being divided by 4. So you are you're getting close. What about other support conditions? If I have a restriction on the pile cap and at the base, then I will have an effective length of just L. Okay, so beta will be simply 1. That's because I haven't drawn that fully there. I can show you. So what we're saying is this guy is here is not allowed to rotate. You can only translate, which means I can only deform this like that. So this still has to be 90 degrees. So if I continue this, reflect this onto the top. So this, it should be symmetric about that axis, and you measure the length distance between the points of contraflexure, and that turns out to be L. So this is how you do it using mode shapes. No calculations needed. Cambridge undergraduates are particularly poor in working out the algebra, so we tend to give them graphical ways of drawing these things. Once you get the mode shape idea into your head, because we're coming from dynamics, this makes more sense. It's exactly working out Euler's buckling loads is exactly the same eigenvalue calculation you do as you do for your dynamic analysis. As I said before, if I would draw the full board shape for full pinned joints, you will get 2. There will be other cases also where I'm allowed no movement and no rotation. Here I'm allowing this thing to displace but no rotation, right? So it's translated there, but theta is 0. And this can be the case when I have more than one pile. If I have a few piles in a pile group, then it's quite hard for the pile cap to rotate. We talked about this briefly yesterday also. So you need to be aware of what is the restriction you are imposing onto your structure. In this case, the pile cap. If I fix everything like a strut, so no delta is 0 and theta is 0, the only thing the pile can do is that, right? So my that will be L1. So try draw the deflected shape you get, measure the distance between points of contraflexure. That should give you your effective length quite easily. Beta is an easy way to do formalize that. But this can be done for all kinds of combinations. For example, if I allow this to partially rotate, then if I can draw the shape, then I can get the beta value for it.
Sir,
Yeah.
sir, being at the base condition, right? Can you give me some realistic example?
Okay. Yeah. For example, if you've driven the pile and your contractor has said you reach refusal, but you haven't. Yeah. So how is this pile going to provide any rotational support? It can't. So once all this stuff liquefies and it wants to buckle, it'll basically do this, only, right? So this. So it's quite easy to actually accidentally reach that pin at the base condition. Any questions on this? So for a given variety of boundary conditions, are you confident? I'm going to set you an example this afternoon, which you probably want to solve. So if you're not sure, now is the good time to ask how to get the value of beta.
So for all support conditions, they are same as Euler's.
So, sorry?
For all support conditions of file, Euler's formulae, whichever are standard, they are all applicable.
Yeah. I mean, we're still treating it like a strut, so obviously they should work. What we are not doing here, and that's the research part of this, is what will the liquefied soil do. Here, this calculation is assuming there's no soil. We're taking soil mechanics out of file design, which is a bit not so good for us, but it's an easy calculation to do. I'll show you how it gets complicated when I add the soil part. Now you understand the background of this buckling. Let's see if it actually happens. Okay, because we saw some buildings which collapsed, bridges which collapsed, and we have a theory for it. We haven't got the proof that it actually happens. To have the proof, Shubi and myself, we had a go at basically having 2 or 3 piles with different pile height loads and shake at the base. We know the pore pressures, we can measure the pore pressures, accelerations, and the rest of the stuff I've been talking about. But this is a very easy experiment to do. All we needed was loose sand and a centrifuge and a shaker. So he got himself these loads made, which are obviously brass loads and on aluminum pipes, and then he filled with sand. I'm showing you post-test behavior, and this is what happened to them. So they all buckled. And as you are excavating. This is after the test. Got some more pictures. Some actually lost their heads as well. Some were still hanging on to the loading file cab. And here is a picture taken immediately after the test, where you can see the sand boils. I told you sand boils are a clear indication of liquefaction. So that was good. But we can also, we don't rely on just the sand boils. We measure the pore pressures at different depths. So we can see how the pore pressure is built up in the soil. So clearly, as we should, the pore pressure builds up. The deeper ones get to a higher pore pressure. The shallow ones can't obviously go to the highest. You can only mobilize enough pore pressure until your effective stress becomes zero. After that, there's nothing the soil can do. But when we started extracting the piles, there's a problem. And this is where me and my student fell apart. Because he said, this is proof enough that the piles are buckling, and it's a problem, to which I agree. But there's a one subtle point which I wanted him to look at is how come these piles are all buckling at the top? I've shown you the other ones as well. They're all trying to buckle by forming a hinge, as you can see, almost 3/4 of the way up. Now, conventional structural analysis will tell you if I have a cantilever and I'm applying a buckling load, the buckling mode for this has to be like this. I'm still maintaining my vertical load. And if you plot the bending moment for this, you will, or invariably before it's going there, you'll invariably get a bending moment which is increasing by that. Yes? Which means the largest bending moment must be here. If the largest bending moment is at the base and it increases as the pile buckles more and more, how the hell the plastic is formed up there and not down here? So this is where it's important to do the experiment, but also take due cognizance of what the experiment is trying to tell you. If you already predetermined that, well, I designed this test for buckling and it did buckle and walk away, you won't nearly learn as much as you should. This is very weird, isn't it? It cannot possibly be true from pure structural calculations we have done that the hinge is forming up there. Now, why is the question? Why it is because soil. We cannot simply wipe out this loose sand. It is there. It's liquefied. We have proved that it is liquefied, but it's still there. Now, one theory is that as the pile, I think this got a bit messy. Let me tidy it up. Now, if the pile is trying to do that, it has to push the soil here away from its path. And if you do that, someone is wake up. Nodding. I thought you're nodding away, so I thought we will wake you up. If you move the pile into the liquefied soil, the initial thinking people had was it's liquefied. What can it do? It's like liquid. Liquid does not offer any resistance, not much anyhow. It turns out that if you take liquefied soil and shear it, it will go hard on you. There's a good reason why it is, but you need to know basics of critical state soil mechanics. If I'm plotting on QP dash, that's my critical state line. I start, cycle down, and come to full liquefaction. So this is where my soil state is after the ground has liquefied. As the pile tries to apply shear stress, so we're asking it to do that. The only way the soil can respond to this is say, right, I can't, I'm already here. And you're asking me to go up this way, and I can't go that way. I have to go along with the critical state line, maybe up to here. If it is going up here, that means my P dash from being approximately 0 here is going to be some value, x kVA. Yes? If how can it increase its P dash? It can't do anything about the total stress. Total stress is what it is. So only way it can do that is by creating suction. So the pore pressures in the region of soil here must be falling to create a suction to satisfy this. And this is why you need to strongly believe in the critical state framework. If the critical state tells you that's what the soil will do, it has to do that. And now you bring that thought back with you. So my P dash is now going up, not because the total stress is changing, but because my soil is going into suction. Then this is getting stronger. Yeah, the soil as the pile starts to move will try to get stronger and oppose the movement of the pile. Now, so we understand that part of it. Now, why did it buckle up here? It still did that. So, our working theory is that the pile wants to do that. It tries every level. First, it wants to form a hinge there. It wants to go that way. The soil gets a snap. I'm at really high confining pressure. I can mobilize quite a lot of, I can go quite high up on this, which means I'll get quite a lot of suction, and you're not going anywhere. And it says, okay, I'll try here. Soil says no. So it works its way up, 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 until a point where it's easy for the water on the surface to come in to destroy my suction. And once the water is, the drainage distance is close enough, that I can't keep my suction that's needed to hold the pile in place. Okay? So it says, right, now you can have a go, and my pile, that's what's going on there. So that one picture there to explain took us about 4 months of scratching heads and working this logic again and again and again. But now we got there, I feel quite chuffed that, it all makes sense. So you will form a plastic hinge according to the rules of plasticity in the pile. However, where that hinge forms is dictated by the liquefied soil. So the lesson we learned is liquefied soil is not going to behave like a liquid. It is a shear dilating, shear hardening material when you apply, when you force it to shear. An equivalent example is human blood. If you take human blood, which is obviously liquid, if you apply big shear to it, it will go thin. our liquefied soil is opposite of that. If you take the liquefied soil and shear it, it will go hard or stiff. Okay, the shear thinning property of human blood is important. The reason we are all alive is because of that. But anyhow, I'm not going to take a biology class. That's something else. Uh, Interesting as they are, materials can be thixotropic. Any questions? So I've thrown quite a lot at you, not using equations, but pure logic. We're just going step by step through this. And there's some background theory for it. Yeah,
When I drive files in the site, it's hardly, straight. It is always imperfect.
yes,
So how do you account for imperfections in the file design process?
absolutely. One of the things I was looking at was people all know that file wander is a thing, and you can get the base of the file to be maybe several feet away from the initial alignment. Now, you need to think about what can happen when the ground liquefies. Are you storing strain energy in these files as you go away from the initial? Obviously, if it's bending, there is strain energy built up in the file. It is possible that once you start liquefying the soil, it will ping back. We have no idea. There is, as I said, there's no experiments in the world that have done or field studies where you can see this. The whole point about all this is that we uh, we can create some of these things. But by all means, if some bright student was to come and say, I want to look at misalignment of files and what happens to them post liquefaction, that's a good topic. We can certainly drive files inclined in flight because we have the actuators to do that and shake it and see if they change alignment. In fact, the instrumentation now is much better. We can attach MEMS accelerometers on the file, which act like an inclinometer. So we know where the file has gone, and you liquefy, see whether it pings back or not.
So like in your reconnaissance, like after post-earthquake reconnaissance,
Yeah.
you observe the files.
Yeah,
Are they straight or are they?
no, I mean, when they pull them out, they're not straight. But that's the problem with field or case histories of field studies is you don't have all the information you like to have. You don't know whether some of those cracks in those concrete piles happened when they were driving them, or whether they're cause of the earthquake. They don't have pore pressure measurements. So it's you need to construct the best picture. A good example is when Ray Seed came to the Bhuj earthquake after the earthquake, and there were no earthquake records because the one seismograph they had, uh, they set the gains on it wrong because they never expected the earthquake to be so big and so close. So when the earthquake happened, it saturated. I attended an IGC conference in Allahabad after that, and there was some person, I forget his name, good job, otherwise I'll just raise my blood pressure. He was trying to tell us that you can get the signal back from a saturated measurement record you have from the seismograph. And I said, there's no way in the world you can do that. If you saturated your signal, you lost it. There's nothing you can do. Go set your gains properly for the next earthquake and wait for the next 25 years before that. But what Ray Seed did was to look at the blocks of rock on the top of temples and other monuments in Burj and see how much they slid or whether they toppled or not, and try to work out the accelerations that way. So peak ground accelerations of about 0.5, zero point 0.4 were what he calculated properly. But it's not like having a seismograph. Go. Now it's much better. I think we've got so many arrays established everywhere in the world, but also in India. So both in Northeast and in Gujarat area, we got good arrays. Okay. I promised you I'll give you a lesson in I, in buckling first. I'm not sure whether have you ever used or come across Penny Robertson's equation? You have. Oh, good.
Still data.
Yeah, yeah. But doesn't matter. But there's much silence across the class, so I'll just explain it quickly. When you do this buckling calculation using the Euler equation is very simple. It only ever worries about pure axial load. Now, everybody in construction knows that there's no such thing as pure axial load. Your loads are always have some eccentricity. Your piles are never straight, either because of the pile bonder or uh, even columns are not that straight. You'll have some imperfection. What Perry Robertson have done is looked at the effect of this uh, imperfection and work out how that changes the buckling load. And these two guys are from my university. So they've done this work in 1970s or 60s, quite long time ago. But it kind of is quite good. What we're seeing here, let's see if I have a I need to explain this. If I take a column, so let's just look at columns and I'm applying, say, an eccentric load. That's the central line, and the vertical load is some distance away. Also, I may have some imperfections in the column itself. If you do that, you calculate your Euler load using your standard equation. And if I plot that for various unsupported lines, this red line is the Euler load, vertical load by Euler calculation. It's going up as your unsupported length is more, it comes down to maybe 1,000 kilonewtons. For some, here I chose just a zero point 0.6 meter diameter pipe or column. However, you also reach, just because of the material, you'll have some limit on the yield of the material. So that is marked by this blue line. That does not change depending on the unsupported length. Every element gets compressed and it can reach yield in compression, right? So that marks the top limit of what the material can take. So you can see beyond a certain length, the column is so short, it can't buckle, it will simply yield in compression. So I should just remind me if I try to draw on here, they'll kill me. That's your working envelope. So you can't reach these points because you reach material yield. Does that make sense? Yeah. Here is compression, this is buckling. Now, what you can do is between the two, you can have this eta, which is a function of eccentricity and imperfections. So if I put all of that as a eta, then I can plot this green line which runs between the two. So the more eccentricity I have, I'll drop my Euler load by that much. So it is important to allow for these eccentricities, especially when we are dealing with applying these to piles, because we know our column loads are never so axial to the pile, and piles themselves have pile bonder. So one of the ways we thought we could handle pile bonder is by bringing that into E and call that the imperfection in the structure. Okay. But this is all we have done for single pile. Now, either you need to be silly like the Japanese show bridge design, or it's very rare that piles are ever used as a single pile. There are the odd occasions, and there are large diameter piles like monopiles, but we'll leave them to one side. But most common application of piles is with pile groups, maybe 2 by 2, 3 by 3, whatever the load demands you. Then you need to think about how these uh, pile groups can fare. And this is where it's important that we understand kinematically admissible mechanisms. Now, if I have a 2 by 2 pile group and I draw the cross section of it, it is possible if I allow the pile cap to translate but won't allow it to rotate because it has rotational stiffness coming from the superstructure, as I discussed yesterday, then you will have a 4-pin mechanism, which will be kinematically admissible. You understand what kinematically admissible means, right? So it's possible for it to move that way. That's all it means. So you'll get this mechanism shown on the left here. So one hinge there, one hinge there, one hinge there, and one hinge there. So that's a possible mechanism. Now, depending upon what I said in terms of shear dilation, the location of these hinges can move up, but still it will be a 4-hinge mechanism. So don't take literally that this is where the hinges will form at the interface between liquefiable soil and the stiff soil. Not true. They can go up because of the dilation effects in the soil, or they can move down if my fixity is not, this is not rock, if it is more pliable material like sands, then it might move down. And Andrew Bohn's expressions can come in handy. The other possibility is I may only need 3 hinges if I allow the rotation of my pile cap. So then I can have 1 hinge there, 1 hinge there, and 1 hinge there, and I don't need 1 here. So these are some of the kinematic admissible mechanisms. There are some more in the book, which I see you have nicely copied and bound. But if I ask you which of these is possible, what would you say? How do you know whether it's going to be a 4-pin mechanism or a 3-pin mechanism? What governs that?
Connection between piles and piles.
Sorry?
Depends on the connection between the piles and the piles.
Good. That's good. So structurally, it depends on how well you connected the piles on the pile cap. Also, structurally, it depends on whether the pile cap is able to rotate. Okay, so that's good. Then we thought we need some proof that when we have these 2 by 2 pile groups, this pile buckling is actually possible. Now, Shubi's work I showed earlier was all on single piles. And he still goes around the world presenting this paper in various guises. There must be 20 or 30 different papers he's written exactly on file per click. But good for him. But his actual PhD thesis was on single file. So I had another student called Jonathan Knapp, who's a professor at Dundee now, and this guy looked at 2 by 2 file. Now, very quickly we realized that to get to buckling loads on a 2 by 2 file group, we have to put quite a lot of load on the top. Now, if I put a lot of load on the top and shake it, I need to worry about, from yesterday's lesson, inertial effects on the file group. They become so big that they can simply, it's like holding the head of the file group and doing that. It'll just break its neck. Not very pleasant for the file group. So we decided to support the file groups in the direction of shaking. This is a very unusual test to do. So we are shaking in this direction, but the file heads can't move. There are supports on either side. And we have PTFE so that the file group can slide in and out of the plane of the paper. So that's how we got rid of the inertial effects. Otherwise, every time we do this test, the files will simply break in under inertial load. And let me show you the picture, then I can come back. So if you see here, you can see a lightly loaded one deformed a bit and stopped, and the more heavily loaded one completely fell off. So we are looking in plan view, and the shaking is in this direction, and these are allowed to go whichever way. And we are able to measure the displacements and accelerations as well. So now we know how they are faring. If I look at the pore pressures in the free field, okay, they liquefy. So the earthquake is only up to here, and they generate the full pore pressure and stay liquefied. Here is when the file cap fell and hit the container. There's a shock, and they can measure that also. So this is the exact event when the big one fell on, and you can still record the shock coming from that. But what's most intriguing for me is this one. This guy, 10952 or whatever you call it, number, is here. So this pore pressure transducer is next to the pile of the heavily loaded one. So you can see as the pile is trying to go away, it's generating that suction. In fact, it has gone to absolute suction. And this now is the proof we were looking for, that the material next to the pile will go into strong dilation. And that suction is what resists the movement of the pile. In this case, the pile cap is so heavy, it could not stop it from falling over, but it tried. It tried its hardest. Before the water moved in, the pore pressure is built up, and there's nothing it can do anymore because the earthquake is finished by now. So we now have the proof of all the stuff I was talking about earlier. Look at the displacements. This is the classical case of what a structural engineer would call instability or any other instability. So you start by deforming a little bit, and then it kind of, the soil tried to stop it from going, and then it said, oh, this is way too much, and runs off. The only reason it stopped there is because our instrument lost contact. Okay, so it's not that it stopped moving then, it's just our instrument can only have a certain range. It recorded up to 1.3 meters prototype scale, so that's more than enough to declare pile dead. By that time, the pile group has died. If anything moves 1.5 meters, your building ain't standing up. But the important thing we want to see here is this verticality of the line. That is why we call this an instability. It's a runaway failure. Once you're in that mode, there's no stop. It's just going to go. And we put out this pipe. Of course, unlike uh, real failures, it's very easy for us to dig out our pipe. We just dig the soil up and get it out. And we got this classical picture of which I'm so proud of. We use it on the book as well. Now count the hinges. How many hinges are formed? Really, one there, and one there, and maybe partially there. So this is reality. In theory, you can idealize the hinges quite nicely, but you can have partial hinges also, where some energy is displayed. So the lesson we learned from all this is that the hinges will form according to the plastic work equation. So you know the energy you need to dissipate, and you know it'll form the minimum number of hinges that's required to dissipate that energy. Sticking very much to the upper bound and lower bound theorems of plasticity. So it all fits nicely to the Cambridge model. Critical states on mechanics is respected, our upper bound, lower bound theories are respected. Perfect. Okay. I think 10:50 is when we stop for tea. Yeah? Okay. We now stop. Then when we come back, I'll show you some of the things you can have a go in terms of numerical analysis of these and what are the pitfalls and difficulties. Okay. Yesterday I was asked briefly by one of you saying that when I covered buckling, can I do something about the base conditions? Have I done enough, or do you want any more? If you want any more, I mean, if you have a question, feel free to ask. But I deliberately went slowly at that part so that everybody understands how to draw those buckling motions. But if you have any questions, now or after tea, you can come and ask me. Okay, that's great. It's very good to have a structural engineer.